Good afternoon and welcome to Hand Wavy Chemistry. Today's video was requested by YouTube user Melissa Silva and it deals with the topic of resonance. In the video Formal Charge and Oxidation Number, we discussed ozone and I told you that it has an oxidation number of 0, but the formal charge for each of the oxygen atoms are different. Here we have a 0, a positive 1, and a negative 1 for the formal charge. However, what I didn't mention was that the lone pair on that terminal oxygen could move in to make a double bond, and at the same time, the two electrons in the double bond could move out to form a lone pair, generating a equally valid structure. And for this other form, that lone pair could move back, recreating the double bond, and the electrons from that double bond could move back out, recreating the lone pair. We effectively have two forms, both with valid Lewis dot structures that are able to move back and forth between each other. And this is what is known as resonance. And it is not just restricted to ozone. We also see resonance in dinitrogen monoxide and in the thiocyanate ion. And it can get even more complex. For example, the carbonate anion, it has 3 different resonance structures that we could draw. And if we were to do something like a sulfate with an expanded octet, there we would get up to having 6 resonance structures. Another way to represent these multiple possible structures is to show the bonds as being spread across the molecule. So in the case of ozone, it would look like this, where that dashed line represents kind of like half a bond on each side. And in this hybridized form, we would now have formal charges of -1/2, +1, and -1/2. We can even have resonance structures involving a ring. For example, benzene. We could draw it as a series of alternating double and single bonds. But all those double bonds could move around one space, creating an equally valid but different structure. So the question becomes, when we have resonance, is it that there are two distinct forms rapidly interconverting back and forth, or are the electrons and the bonds spread and hybridized across the molecule? In 1899, the first suggestion that resonance was actually to do with spreading electrons was made, and it was in relation to the unusual stability of benzene. Alkenes are usually able to undergo addition reactions, where atoms are added across the double bond. But this was not the case with benzene. Benzene instead underwent substitution reactions. You had to remove an atom to put in a new one. The double bonds were still present after the reaction. Molecular orbital theory would predict a delocalized pi system, and we can make calculations and predictions about the different energy levels associated with these delocalized systems. But molecular orbital theory is not the only type of bonding theory. So the validity of these predictions and measurements depend on how accurate the assumptions made in molecular orbital theory are. And there are other bits of experimental and analytical evidence that all suggest that resonance is delocalized. But the absolute best bit of evidence that shows delocalization as a result of resonance comes from X-ray crystallography. X-ray crystallography is a technique that displays the images of molecules. We see the relative positions of the atoms within space, and we can measure the distances between them. From X-ray crystal measurements, we are able to see that a carbon-carbon single bond is about 155 picometers in length, and a carbon-carbon double bond is about 133 picometers in length. So if a benzene ring or a similar delocalized system was made up of alternating single and double bonds, we would expect to see about 155 picometers, 133, 155, 133, and so on around the ring. However, look at this tyrosine molecule. As we move around looking at the distances between the carbon atoms, we see approximately 140 picometers for each and every bond. They are all exactly the same length, and each one is longer than a double bond, but shorter than a single bond. And in case you're wondering if this is just a result of the technique averaging out all the different positions, I want to show you now a different crystal structure. At one end of this molecule, we have a delocalized system, which is flat. Meanwhile, at the other end, you can see something weird is going on. There seem to be overlapping carbon atoms. And that is because at that end of the molecule, we're going to have one of the carbons above the plane of the ring and the other below it. And they could be either way. X-ray crystallography sees each form and can even tell us about what the relative abundances of each are. And that's not all X-ray crystallography can tell us. It can also start to highlight intermolecular interactions and tell us more about how molecules pack together. But that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.